Good morning, everybody. In Persian, salam. I'd like to appreciate all the organizers of this first International Conference of Holography and its applications. In my talk today, I will try to address the origin of holography principle, its applications as a potential candidate, especially for dark energy, then the advantages and disadvantages of such an interpretation. Let me read a quotation of Professor Ethoff. He said, first of all, be serious about it. Be serious about it on your way towards becoming a bad theoretician. Take your own amateur theory, stop checking it for mistakes, don't listen to colleagues who do spot weaknesses, and start admiring your own infallible intelligence. Okay, today I will go through investigating the mathematics of holography principle utilizing the so-called dimensional analysis at first, and hereafter I call it the analysis. I will also discuss how this relates to the holographic dark energy models. Certainly, the study of emergent models of these concepts also will be interesting, and we will have a little observational discussion, especially with the help of electron and muon gyromagnetic anomaly. Okay. Here, I want to find a relationship between different properties of black holes, say, for example, area and entropy. And in doing so, we employed the so-called D analysis, which contains the speed of light, the gravitational constant, and the Planck constant, Boltzmann constant, and some other fundamental constants in physics. And by considering the no-hair theorem, and for the simplest class of black holes, that is the Schwarzschild one, we can consider m as mass, g and gravitational constant, and c as the speed of light for our analysis. According to classical mechanics, we know the area of the black hole will never decrease, and it reminds us another important physical law of thermodynamics, in other words, the entropy. But what we can say about the entropy of a black hole, in which swallow a lot of information with no way to escape, and it has some same external state with lots of possible internal states, and accordingly a large entropy. But how large? Here, by solving these simultaneous equations, and only by using the analysis, one can obtain a relation for area of event horizon based on fundamental constant in physics. It's very close to the Hawking relation. It was in 1972, Jacob Bekenstein proposed that it makes sense if one consider entropy proportional to the area of the event horizon of the black hole. He suggested, for example, S can be considered as this equation, eta A. And at first step, therefore, we need to determine the dimension of entropy. Then again, by considering the dimensional analysis, we can determine eta. In this regard, one can consider G, C, H bar, and KB, the Boltzmann constant. Then by virtue of dimension of eta and establishing such equality and some same equations, you see here, maybe we can find a relationship for the entropy by solving these simultaneous equations again, and the entropy is very close to Using this dimensional analysis is very close to its main approach based on quantum theory of gravity. Maybe also we can consider the Hawking temperature here. And according to Boltzmann, the entropy of the system relates the microstates of the system. Therefore, for a black hole, one can realize that it has microstructure. The presence of G and H bar in entropy suggests that this black hole maybe has something to do with quantum theory of gravity. Utilizing these phenomena, we can find a way to understand the Hawking radiation. It was in 1974, Stephen Hawking discovered remarkable facts about the universe. Black holes glow. It means they radiate and eventually disappear due to this radiation. For a black hole and its event horizon, we can assign an absolute temperature to do the black hole's analysis, and usually we can call it Hawking temperature. Now, by introducing the first law of thermodynamics and the Einstein famous equation, E is equal to mc squared, one has T as a function like c squared times by ds to the m, the entropy to the mass, 2 minus 1. But already we found a relationship between event horizon area and mass, then ds to the m can be considered as this green equation here. This equation for Hawking temperature shows a black hole temperature increases as it radiates its mass. It is unlike many other ordinary objects in the universe. For the smallest stellar black hole, this temperature can be calculated, and it's around 2 times 10 to minus 8 Kelvin. And by doing some simple calculations, evaporation time for such black hole is around 10 to 68 years and exceeds is much more larger than the age of the universe. Here also one can go a little bit more deeply through one of the immediate consequences of Hawking radiation.
Sorry, Haidar. Seems your slide is frozen.
Oh, no. Still, I'm on 5.
Just the first.
Yes, Stephen Hawking showed this relation has no memory. This temperature, I mean, has no memory, and therefore it seems the information has been lost, apparently, a little bit. On the other side, from unitarity principle of quantum mechanics, we know such system and the information of such system cannot be created or destroyed when it evolves in time. And it is the so-called information paradox. One possible solution to overcome this contradiction is known as the holographic principle. The principle suggests that the information content of a black hole is somehow encoded on the event horizon of the black hole. Based on the Bekenstein-Hawking entropy, one can find that entropy is proportional to the n. What is n? The number of simplest possible area based on the Planck length, which is known as Planck pixels. We can imagine each cell is equal to 1 bit in information language, and one cell has 2 states, 0 or 1, for instance. And for n cells, we have 2 to n different states. Okay. According to Boltzmann again, entropy of system is proportional to Boltzmann constant times logarithm of microstates. Here you see this green equation. And if the number of microstates will reach 2 to n for a tiny black hole at the size of a proton, the number of the bits is 10 to 31 gigabytes, and it contains more information than all the world computers, which is of the order of 10 to 12 gigabytes. So it's very huge capacity for a black hole, tiny black hole. And here you can see a quotation again, but this time from the inventor of this principle, Leonard Susskind. The universe filled with galaxies, stars, planets, houses, boulders, and people is a hologram. Okay, for the friends that my slides was frozen, quickly I can click on this PDF format of my slides. Here I wanted to obtain a relationship between the area of a black hole and also the entropy of the black hole using the so-called D analysis, and considering the Bekenstein proposal, I obtained such relationships between the entropy and also the surface of the event horizon of the black hole. And here I established a relationship between the temperature of the black hole and also the entropy. And using these facts, I could establish a relationship between information theory and also the entropy of the black hole based on the microstates inside the black hole. Okay, and here you can see that entropy is equal to the n, which n is the number of the microstates of the black hole, and is equal to the surface of the black hole based on the micro, maybe smallest areas that we can imagine for the black holes. It can be interested for the quantum gravitists. And here, as I said, this is a quotation from the Leonard Susskind, one of the inventors of the holographic principle. He wrote, the universe filled with galaxies, stars, planets, houses, boulders, and people is a hologram, an image of reality coded on a distant two-dimensional surface. So then I can go to next slide. And sorry, just I want to check, Behnam, right now my slide is working, yes?
Yes. Okay.
Okay, thank you so much. Thank you so much. So right now I want to jump to my main topic of my talk. But considering the holographic principle and to get rid of the UV IR cutoffs problems appears in very high energy quantum field theory, Cohen and his colleagues Kaplan and also Nelson in 1999 in a paper which appeared in PRL proposed an effective version of field theory that UV and IR cutoffs are not independently changing anymore. For an effective field theory, and according to Gerard et Hooft, in a box of size of L with UV cutoff lambda, the entropy scales extensively, L cubed, lambda cubed. However, the peculiar and strange thermodynamics of black holes and Bekenstein's proposal led him to postulate that Bekenstein to postulate that the maximum entropy in a box of volume L cubed behaves non-extensively. But what does it mean? It means the entropy growing only as the area of the box. It was a strange result. To avoid any difficulties, appeared in effective field theories, the Bekenstein entropy bound may be satisfied if one limit the volume of the system according to this Cyan equation. You see this equation here. L cubed, lambda cubed, smaller than the entropy of the black hole, and it was based on the L squared and Planck squares. And it was proposed to overcome the difficulties which appeared in 1 plus 3 dimensions in high energy physics. After some manipulation of equations, Cohen and his colleagues have obtained this green limit for the size of the box and also the energy content in this box, which could be considered smaller than L, which is the size, IR cutoff, and also M Planck squared. In some sense, one can consider the maximum of entropy as S of black hole to 3/4. Maybe I will show in next slide. Maybe they made a blunder here in these definitions. But some people later, maybe one of them was Lee in physics letters B in 2004, proposed such relationship for the energy contents of the box or of our universe, we can imagine, and he showed the content based on the 0-point quantum fluctuations could be obtained as M Planck squared over by L squared. And this is the start point of holographic dark energy. Okay, slide 9. But we know, according to 0-point quantum fluctuations of a system, lambda to 4 can be interpreted as the content of energy of the system. This is a true fact. For the cosmological purpose, it can be also interpreted as the dark energy. But also some scientists show that maybe we cannot consider whole the 0-point quantum fluctuations as the whole the dark energy content of the universe. The dark energy content of the system, it was maybe Maggiore in 2011 showed that it's just around 10% of whole the dark energy can be considered as the 0-point quantum fluctuations. Here, by means of concepts like holographic dark energy, Bekenstein entropy, and other extended entropies, Kai in 2007 proposed this model, like age-graphic dark energy, as our first speaker noted in his talk, that instead of length of the universe, we can consider the time, cosmic time, and also again to overcome with the problems that age-graphic dark energy faced in determining the matter domination universe. When in 2008 they proposed another model they named new age-graphic dark energy. But also I will show all of these models which they originated from the holographic principle, maybe they are ill, they are sick models. And also you can see an entropy corrected holographic dark energy, again based on the corrected entropy of the black holes. But maybe I showed they have problems. Okay. But in order to perform an effective field theory calculations, we maybe simultaneously impose UV and IR cutoff consistent with the entropy bound appeared in last slides. There will be some small discrepancies and also like anomalies between such calculations and also conventional calculations, one performed in an infinite box. For example, you can consider an infinite box and also an finite box with the cutoffs. Such a discrepancy can be of interest when trying to discover new physics. For example, for radiative experiments and also radiative quantum field theory. When you want to invent new physics, you need to examine your results. And one of those important tests, one can consider G-2 test for the electron and muon gyromagnetic anomalies. They can be the matter of interest. For example, consider this G-2 anomaly for electron, the UV and IR cutoffs that we must impose each these limits on one of them separately, but simultaneously, lead to corrections to the usual calculation. Whose total size is d G-2. This is the total size of the corrections to the G-2 anomaly. And whereas lambda is of the order of 14 TeV, one can obtain a relationship for the size of these corrections. For example, for the electron, lambda and L can be obtained and of these contents. But I borrowed these quantities from the Cohen and his colleagues' papers. One of them is 1999, and also the recent paper in which still an archive, and there was no the published version of the paper. Okay. And here you can see.
Sorry, you have
it's just some
5 minutes.
Oh, okay, I will finish it. And there is some statistics of the publication of the papers based on the archive database from 1994 to 2022, which you can see the holography principle has much more attracted much more papers to itself, and also age-graphic dark energy and holographic dark energy. I just wanted to show the activities based on these concepts. But as I said and indicated, despite all the advantages of holographic dark energy models, some problems should be addressed much more carefully, and I will show you why I say this is a sick model. Maybe there have been various cosmological models proposed exploiting a UV-IR constraint to explain the dark energy. But while they are intriguing and interesting, it would be more compelling to find evidences for the UV-IR constraint in terrestrial experiments. Some experiments on the ground and Earth. Since the most accurate tests of quantum field theory are the G-2 of the electron and muon, it makes sense to consider what happens to the calculation of the theoretical and also experimental results based on the one loop calculations as these Sayan equations, you see. sorry, here, here. These Saiyan equations. You see, I showed the anomalies appeared based on the Schwinger-Keldysh calculations. We can show this anomaly can be obtained as this yellow equation, and then it can be obtained based on these green amounts for the electron and for the mu1. You see? Okay. For the G-2 theoretical results, in my approach, and based on the results appeared in slide 14 and also 13, lambda and L show a different behavior compared to the results of the CKN, I mean Cohen and Kaplan and Nelson papers. For mine, the deviation for the one loop test is of order of 10 to minus 23, which is smaller than the prediction of CKN papers, and comparable to the Bank and Draper paper, which recently they wrote a comment on the CKN paper. The result I obtained is closer to the Bank and Draper paper. But to obtain a quantum gravity prediction, theoretical prediction, maybe it should be smaller than this amount I obtained again. And finally, our main aim of this talk was to check the validity of the proposed holographic dark energy, and the bounds appeared in CKN and CK papers and reports. It has been shown that according to the lattice field theory results and Bekenstein-Hawking entropy, the so-called holographic dark energy, at least in its present form, cannot be claimed anymore. It was also showed that scaling the UV cutoff and also IR cutoff, like the L2 minus 2 and L2 minus 1, is not arbitrary. We should take care of scaling the UV cutoff, because in CKN and CK they considered L2 minus 2, which I showed in my paper that it is not arbitrary. We should take care. One of the immediate consequences of these corrections resulted in some corrections in emergent models of this principle. For example, age-graphic dark energy, holographic dark extended holographic dark energy, entropy-corrected holographic dark energy, and new age-graphic dark energy, which all of them obtained based on these papers by CKN and CK. They should maybe re-examined, and also we have to rewrite them. And also our estimation for the G-2 gyromagnetic electron anomaly at the one loop level is of the order of 10 to minus 23, which has some differences with the CKN prediction. Thank you very much for your attention.